Hello everyone, thanks for joining me today. I'm very excited to share my experience in testing application storage stability by injecting storage errors. I am Keao Yang from PinCap, the company behind two distributed systems, TiDB and TiKV. And also, I am a maintainer of ChaosFS, mainly responsible for the controller framework and the implementation of some kinds of the chaos, one of which is the I/O injection, our topic today. ChaosFS is a chaos engineering platform for Kubernetes. With it, you can simulate network, kernel, I/O errors by simply submitting a YAML file. For example, by applying this IoChaos configuration, the I/O operation on specific paths in all selected containers, or pods if you are familiar with Kubernetes, will be injected with 10 microseconds delay. In this session, I will talk about why the storage error does matter and why it's necessary to simulate storage error and test your application with it. After that, I will introduce the implementation of storage error simulation, both the big pictures and the detailed programs. Okay, let's get on to the first chapter. The storage error does matter. I got a report about hard drive failure rate in 2020 from Backblaze, and it illustrates how frequent the storage error happen. The total average AFR, which means annual failure rate of hard drive, is 0.93%, which means if your cluster has more than 40,000 disks, one of them will break per day. Though the stability of solid drive is much better, it's not good enough. The total ARR, which means annual replacement rate, is 0.22%, according to a study on SSD reliability. What's more, usually the storage failure doesn't occur evenly. The reality you are facing is not that one disk breaks every day, but several hard drives break at the same time, especially when you are rebuilding your RAID array or doing any other recovery or backup operation. And the impact of storage error becomes harder to predict as the system becomes much more complicated than several years ago. A simple disk error will cause corruption in the file system, and the file system will throw an error to the application, which is part of the service. And the service will cause an error on other services. And finally, transmit this storage error to the front-end user. Every step of the error transmission process is too hard to do static analysis. For example, in reality, different file systems and different storage errors at different places will have different expressions. This table is captured from a paper entitled Evaluating File System Reliability on SSD. In this paper, the researchers inject error to the file system low-level data structures to say what will happen to the file system and whether it can be fixed automatically if the storage layer is unreliable. And the internal services usually have a really chaotic dependency relationship globally. It could be counterintuitive so that you will never know what will happen without injecting error intentionally, which is also the main idea of chaos engineering and is the main idea of this talk. After trying to convince you the storage error simulation does matter, let's come to the next chapter, where I will talk about how it's implemented inside the ChaosFS and how we, the developers of ChaosFS, make it easy to use. It's a little tricky and related to many interesting aspects such as file systems, the container, and the namespace in Linux. the runtime code injection technology, and many other technologies. They have brought me a fantastic trip during the development, and that is exactly what I want to share with you today. If you want to inject error into something, I believe this is always the roadmap to find a solution. First, let's investigate and learn the normal execution paths, and then find whether there are some steps to inject errors. For example, here is the normal I/O routine on Linux. A user space application calls the system calls, passes the page cache, and comes to the VFS layers. The VFS abstraction will lead the call to the real file system implementation. For example, the ext4 file system implementation. The file system will read or write on the block device, and finally read or write on the physical device. Among these layers, there are several options to inject. For example, from the upper level to the bottom level, we can inject errors through system call hooks, or through customized file systems, or provide an injected driver, or even build a chaotic physical device. The error simulation on a lower level usually has better effects and is more realistic, but is also more expensive. Our choice is to develop a customized file system and use it to inject errors. To make it easier to install and use, we build this file system on fields. After mounting our ChaosFS on a path, all I/O operation inside the path will become a fields request to the ChaosFS process. And the ChaosFS will follow the instructions from the system and do the same I/O operation on another folder. For example, assuming the ChaosFS is mounted as mount data1, a read request for the mount data1 hello.txt arrives. The implementation of ChaosFS will read from the mount data1 ChaosFS hello.txt to get the real content and send it as the response. Besides simply mirroring the I/O operation, it will inject delays or errors before sending back the response. Developing such a chaos file system is not a simple thing as it sounds. It's required to be safe and with low overhead, so we choose to adapt Rust language to ensure the safety of our implementation. It also should provide rich error injections like delay or data corruption or attributes and metadata error. What's most important, it should be multi-threaded and asynchronously to inject delay, even without considering the performance. For example, if you want to inject 10 microseconds delay for 50% request, if the file system waits for 10 microseconds synchronously, some other request will be blocked, and the total latency could be much more than 5 microseconds on average. However, if the wait is asynchronously on multi-threads, the file system is able to handle other requests during the delay, so other requests will not be blocked and get the real 5 microseconds delay in average. After implementing this chaos file system, we should move the original path to a new path with ChaosFS appended to it, and mount the ChaosFS to the original path so that you do not need to modify the application in the container. The next time the application opens the file system and opens the file under this path, it will open the file in the chaos file system, and the data will be mirrored to the modified path. However, it also brings another problem. If your process is running the open file will not be the one under Keao's file system, but still the one under the original file system, which means all the error injection like delay will not take effect for the already open files. Detailedly speaking, after the application opens a file, it will get an FD points to the file. For example, the 4 points to mount data1 hello.txt. Then the injection program moves the mount point, so the pointed file moves accordingly. The FD4 still points to the original file system. And how we could make it possible to point to the newly injected file system? Let's introduce the dupe2 system call, which plays a key role in our implementation. It will create a copy of the file descriptor old FD using the file descriptor specified in new FD. This system call empowers us to open a file under the specified FD number. With the help of it, we can open the corresponding file under the Keao's file system and get a new file descriptor, for example, the 5 here. And we can use dupe2 5.4 to make the file descriptor 4 point to the newly opened file. The problem is that the first red line of codes are the original program logic inside the application, and the mount move in the blue is the behavior of injection routine. We need the application to run the green part automatically, but obviously the injectees will not contain this logic to replace open files. Executing code and system call in another process address space could be tricky. I'm really happy to hear that a patch on Linux kernel has been submitted to add a system call called process VM execute to run codes under another process address namespace. But obviously, we cannot rely on a thing which hasn't been merged to the main line. So we still use the traditional ptrace way to accomplish this. Firstly, we rewrite these 2 lines into assembly codes and compile them to binary codes. For example, here, and use process VM write_b system call to load them into the target memory space. Finally, use ptrace to modify the IP register and points to the loaded program and let it run automatically. After solving the open files, let's come to the last problem: how to inject into the container, as the container is a technology about isolation and security. The problem is that the ChaosFS program should run inside the target container, but itself doesn't exist in the target container. Here is a similar example. Have you tried to run bash in the container, but sadly find the bash doesn't exist in the target container? ChaosFS is facing the same embarrassing situation. Loading the binary into target container is one possible choice, right? But it's hard to find a way to compatible for all container images and all container runtimes. For example, the kubecontrol copy and the docker copy commands relies on the tar program inside the container image, which is not sure to exist in every images. For example, in the distro-less image, the tar program doesn't exist. And the dependencies are another problem. Loading all related shared libraries into the target container is impossible, as it will ruin the user's environment. Considering all these disadvantages, we choose to load binary from current mount namespace directly, but run in the target namespace. Let's see how it could be possible. ChaosFS solved this problem by running Saturn as the ELF constructor after loading the binary and before entering the entry of the program. When we are executing a binary file, the ld.so descriptor will load the ELF binary to the memory and load related dynamic libraries into the memory. and record the constructor field of them. Before stepping into the entry of the binary file, the ELF constructor of every library will be executed. In the ChaosFS case, while executing the ChaosFS binary, the system will load it onto the memory and decode the ELF file format. After this process, it will load a dynamic library which we call nsexec.so. In this dynamic library, we define the constructor to set ns and enter the target namespace. Finally, the ChaosFS runs in the target namespace and run the injection steps which we have talked about in the former slides. Okay, I think this is all I plan to cover today. If you are interested in the Chaos Mesh project or curious about the technology implementation, you can get more information on our GitHub organization or the Twitter accounts. And you can also get in touch with the developer team of Chaos Mesh on the CNCF Slack channel. Any attempt or thoughts on the chaos engineering and our projects are welcome to share with us. Thank you, and here is our contacts. Anyone has any questions? I'd like to answer if you have.